Hello, everyone. Thank you for attending this bonus workshop, part of the MLOps 2020 Summit. My name is Faraz. I'm one of the main organizers at TMLS. A quick note that you would have received an email from Hopin last night for the conference that is happening tomorrow and day after. Please also check your junk mail. If you haven't received it, you will be receiving a reminder in the afternoon today, and you will also be receiving a reminder later in the evening as well. Today, I'm very excited to introduce our facilitator today, Alexander Wong. Alex Wong is the Chief Scientist at DarwinAI and is also currently the Canadian Research Chair in the area of artificial intelligence. He is also the co-director of the Vision and Image Processing Research Group, and he is also an associate professor in the Department of System Design Engineering at the University of Waterloo. He has published over 550 peer-reviewed journals, and as well as conference papers, as well as patents in various fields such as computational imaging, artificial intelligence, and computer vision. So without further ado, welcome Alex, and over to you.
So thank you very much for the introduction, and thank you for the opportunity to do this workshop. If you can't hear me properly, just let me know whenever. And also I'll be keeping my eye out on the Zoom group chat in case there are any questions. But without further ado, what I'm going to do right now is I'll give you this a workshop on how a human-machine collaboration approach to deep learning development can greatly accelerate the deep learning process. So first, I'm going to give a quick overview into this human-machine collaborative approach. Give a quick overview of the Jensen platform that we've built, and then I'll actually run through a live demo so you can see how we actually use it and do it. So first, just a quick introduction to, I guess, DarwinAI. DarwinAI is a startup out of that came from the University of Waterloo and is currently at Waterloo, Ontario, Canada. And our focus has been around building AI you can trust. We have around 25 plus employees and we work with a large number of enterprises in a variety of different fields, from finance to aerospace to automotive to consumer electronics. And so our main focus has been on how do we actually accelerate the deep learning development process. So just a quick, I guess, overview of the problem that we have at hand, especially working with our different clients. One is that developing enterprise deep learning solutions is just a hard thing to do, right? And there's a number of reasons why. One is just the sheer amount of complexity with doing deep learning development, with the mass amounts of data, huge amount of manual processes, and there's a lot of trial and error to get this together. There's a lot of guesswork involved in building deep learning solutions. And so we're talking about months to years to develop appropriately. So if you somehow manage to build something that is functional and meets your accuracy or requirements, one of the hard parts is now you need to deploy it. So that's where the high computational complexity, cost involved, and investment in server farms are needed for deep learning in the enterprise, whether for the edge or whether for the cloud. And so you've managed to build it, but you can't deploy it. And so suppose you get through both of these hurdles. Now you have the third hurdle, which is a low trust issue, which is there's just a lack of understanding of data quality and how AI, especially deep learning, reaches decisions. So there's whole black box effect. And so one of our goals has been, can we actually tackle all three of these problems to greatly accelerate deep learning development? And so that's the solution that we've built. It's called Gensynth. Short for General Synthesis, and it's an AI-assisted deep learning development platform catered for tackling all three of those problems. One is to accelerate design, So we want to design AI faster through an AI-assisted workflow that allows you to develop highly efficient AI for any use case based on your performance and operational targets in days versus months. And the other thing is that it's able to generate a ready-to-use efficient AI that meets your operational targets so that it can be deployed in any hardware environment, be it cloud, edge, so on and so forth. And finally, because of its inherent understanding of what it's being built, it's able to explain the AI black box. So essentially, it'll be able to allow you to understand how and why AI reaches its decisions so you can build AI you can trust. So those are the three key things that we tackle. And I'm actually going to go run through as to how we do it. And so most of you are familiar, for those who've actually done deep learning development, most of you are familiar with the traditional deep learning development cycle. So first, what you do is you define your use case and define your operational targets. I need to run on this hardware. It needs to achieve a certain level of accuracy. It needs to run this fast. Here's your power requirements. And once you've defined all that, you need to prepare your data set. Then you create your model based on these operational targets. Then you train it up and you hope that it reaches your level of performance. And then you do performance validation to make sure that it's doing the right thing. And then if everything goes perfectly, then you're good to deploy. But in most of these cases, this never happens. So what ends up happening is a cyclical iterative process where you're training different models, doing architecture tuning, you're then validating, verifying, and then if it doesn't meet your requirements, you got to go back. So there's a lot of iterative guesswork involved to getting this done. So it becomes a very long, laborious process, especially because it's very difficult to know exactly what your model parameters should be, what the architecture should be, what your training parameters should be, so on and so forth. So with the human machine collaborative development approach, what we do is we still define our operational targets. We still prepare data the same way. However, what we do is we shift to a more automated human-machine collaborative deep learning paradigm where we treat the underlying AI as a collaborator to the human. So us as humans, we're great at defining requirements. We know what it needs to do. We know how to put together the overall scaffolding of what needs to be done. We know how to prepare the underlying data. But the hard part is the actual final design of a tailored deep neural network solution and how to understand it. So therefore, here, by treating AI as a collaborator, it allows us to feed all that into the AI. Then the AI can learn from it all this information from your model prototypes to your task at hand, to your data, to your operational requirements, and generate better neural networks, right? Through a machine-driven design exploration approach. And because it's able to learn and understand all these neural networks that it's able to build, it's also able to explain it. So here we're trying to automate this process. And it's worked quite well. And we'll actually go through an in-depth look into how we do it. So here is just our Gensim platform in a nutshell that allows us to achieve this human-machine collaborative design. And it is set up in certain phases. So as a developer, as a first phase, what I want to do is once I define my requirements and my use case, what I do is go through a human-driven design prototyping stage where I kind of build a scaffolding or the prototype of what I want to build. I might not be able to hit any of the accuracy requirements or set up perfectly, but that's okay. So once I have that, as well as the task and data at hand, what I can then do is pass it into Gensim for the machine-driven design exploration stage, where Gensim will take all this information, learn from it, and go through a auto model generation phase, where it generates models to meet those operational targets and requirements based on what you provided, as well as on auto model explainability stage, where you're able to then go through exactly why your model made certain decisions, where the errors are, where the biases are, and so on and so forth. So Gensim sits on top of a variety of machine learning frameworks. So it's compatible with TensorFlow and Keras, and Gensim can be deployed either on the cloud, through any of the cloud providers, Or if you want a special level of privacy, as with a lot of our different clients, what you can do is you could have it deployed on premise directly on your local servers. And what Jensen actually generates are ready-to-use models in the form of computational graphs. And any of those can then be deployed, modified however you want, and integrated into your own MLOps environment, and also accelerate through hardware libraries for, we collab with NVIDIA, Intel, ARM, to make sure that whatever we generate are quite custom fit for those particular hardware frameworks. And then you're able to deploy it on any hardware you want. So that's just a high-level overview of what Jensen does and where it sits in your MLOps pipeline. And so just a quick use case before we dive deep into the actual run-through of the platform itself for human-machine collaborative design. So a case study we did was with Audi for rapid development of AI models for autonomous driving. So one of the challenges they had was that they were building an AI system for autonomous driving, but it was just too large to deploy on GPUs and too expensive to do simulation tests, and inference speeds were too slow for safe use. So we're not just talking about safe deployment, we're also talking about running simulation and testing. And so what we did was we worked with them to use Jensen to automatically generate compact deep learning models without compromising prediction accuracy. And the results are quite good. So one is we're able to reduce the time necessary for development by 90% through this automation, through the human-machine collaborative design approach. We're able to generate a model that was 2 times faster than what they had on the target hardware, which allowed them for much greater acceleration and more deployment ready, and also significant cost savings during runtime in the order around $600,000 US. And so what I'm going to do right now is I'm going to stop sharing my screen. And now I'm going to share the actual platform itself and actually do a full run through on how we leverage it for human-machine collaborative design. Hi, please, can you let me know if you can see my screen?
Yep, we can see your screen.
Okay, perfect. So now I'm going to run through, I guess, for me, the more fun part, which is I'm going to do a run through of the Jensen platform and illustrate how we use it to accelerate deep learning development. So what you see here is the Jensen platform itself. You access it through a web interface, and this could be, again, deployed on the cloud. In this case, we're deployed here on AWS, or you could actually have it directly on your private cloud or on your local computer. So you could configure however you want. So the first thing is, as a developer, what I've done is I've kind of created a rough prototype of what I want. I haven't, trained it up. I haven't set it up properly, but I have the data ready. Everything's good to go. So the first step I do, instead of the usual process of iterating, improving, and so forth, that could take months, what I can then do now is I could feed all this information into the Jensen platform. So here we are at the data set manager. This is where we specify the data set that we would like to do. And we create the data interface around it. So here in this case, for this particular illustrated purpose, we're going to create a ImageNet dataset entity. And here illustrate, essentially informs Jensen on how to actually access your underlying data. So we have a fully functional script editor with autocomplete and so on and so forth that you can actually use to set it up. And this is all done in Python. And so once I've set up the dataset entity, what I can then do is actually set up the model entity itself. So we then input all the necessary information pertaining to your model prototype. So here, as you can see, we specify the input tensors, output tensors, so on and so forth, the loss tensors, and so on and so forth, as well as define some of the actually metrics. And here right now, we're going to use accuracy metrics that are baked directly into the model prototype. But in a situation where you have cases where you really need to have a customized performance metric, what we also provide is a performance metric manager where you can actually create any kind of custom performance metric that you want for your specialized use case. So now that we've actually set up all of the key aspects, which is the model prototype, the data entity, as well as the performance metric entity, what we're going to do is we're going to start a new job. So here I'm just going to call it Resonant 50 ImageNet. That's kind of the prototype. And we're trying to use it to create a tailored system for image classification. Again, with GenSniff, it supports a wide variety because it works at the computational graph level. Pretty much any kind of task can be applied in the GenSniff platform. So here in this case, what we're going to do is we're going to specify here, we put in a job name in our new job. And what the GenSniff platform allows you to do is allows you to not only leverage multiple GPUs, but also multiple machines. So here I'm going to select 2 GPUs from our first server machine, and we're going to select another 2 from our second server machine. And so now it's going to do multi-machine, multi-GPU learning. Then what we do is we specify our entities. It's actually quite simple. Because we've already set up the model entities, data set entities, and so on and so forth, here all we have to do is select it from the ones that we created. We also provide a number of pre-created model prototypes, as well as data set entities, so you can actually use as starting points. So here I'm going to select this. So now we're actually good to go. And one of the cool things about this is because each of the models as well as data sets are managed independently, we could essentially mix and match. So it makes it easier for you to perform your experiments that way. For example, I have 10 different model prototypes I like to start off with, and 5 different data sets I could actually mix and match. So then what I do is then I'll continue. And so once I continue, what we can then do is specify the model and the model tensors. So here what I can do is just click and it'll automatically show me the applicable tensors that I can have set up for my model. So for my image, it's from an iterator. For the label, the ground truth itself, it's from a separate iterator. And here I can actually select the model performance metric that I've incorporated. So in this case, I'm going to use a model accuracy tensor, and then I'm going to continue from there. And as the last step, what I can do is now define the learn, build, and explain parameters. So here what I do is I specify essentially how many epochs that I've actually leveraged before when I first created my prototype. GenSniff platform supports fully integrated mixed precision learning, so I'm going to turn that on. And most of this I could leave as a default and continue. And then what GenSniff does is then it will actually learn from your underlying system and your task at hand. It'll automatically find the best way to learn and create new models. And finally, what I'm going to do is I'll specify the operational target that I would like to hit. So in this case, what I'll do is I would like to hit target size ratio for the generated model at around 5% of the original, size of the model prototype. And I'm going to specify that I would like it to hit and maintain a 93% accuracy. And finally, in the last part, what I can do is I could specify and tell it that I would like it to actually learn to explain the decision-making process of my underlying model. And currently we support 2 types. One, we support explainability for classification models and explainability for object detection models. And then what I can do is I could click Start Job. And now what's going to do is GenSniff is going to take all this information and it'll start learning from it. And it'll start learning and generating new models based on your operational targets, requirements, data, and task at hand. So once it gets started, it's going to be shown in the job screen. So here we provide full job management. So you're able to manage each experiment that you do, as well as all of the underlying generated models that are created. And we do it in a very we offer a number of different collaborative features to allow different developers and teams to work together to collaborate on building better deep neural networks. So you're able to see what some of your colleagues are doing if you have permissions for it, or you could share some of your experiments with your colleagues so you can actually, they can leverage your particular model and see your results. So here what we're going to do is we're going to look at the one that we started, which is the ResNet 50. And what you can see now is details on the different models that it was able to generate. So what Jensen does is it'll learn from your information and it'll generate not one, not two, but a number of different models that meet your operational requirements, but with different performance trade-offs. And that's where the human-machine collaborative design really comes into play. You specify what targets it needs to hit. It will then generate ready-to-go models with different trade-offs that meet those requirements. And then you can pick and choose which one is best for your deployment or integration needs for your MLOps pipeline. So here what you can see is it created 6 different models, each exceeding the 93% performance target. And it has different trade-offs. So the last model, as you can see, that it generated meets your requirements, has slightly lower performance than the first few, but is on the order of more than a magnitude smaller and a magnitude faster. So now this allows you to then pick and choose what you want to deploy on the cloud, what you want to deploy on the edge, so on and so forth. And of course, to allow acceleration of your deep learning development, we provide a huge amount of transparency. So what we want, if you click on any one of those, what you can do is you could actually then take these generated models and then generate new edge-ready models if you want to deploy on the edge. You could fine-tune it further if you want. You could branch off a different experiment if you want. Or the other thing is that you could actually just download the model and it comes in the form of a computational graph, so you could further modify it, extend upon it, integrate into your system. It's all yours to keep and do. And so what I mean before in terms of greater transparency is that the underlying AI system of the Jensen platform will actually allow you to not just look at high-level details like this, but it'll actually does a full comparative analysis. So the underlying AI will decompose all of the models that it generates for you and allows you to then look at the different flops distributions, the channel distribution, parameter distribution, and so on and so forth. But the other key thing is the underlying AI will also highlight performance bottlenecks so that you can actually see how it's improving and where the bottlenecks lie, so you have a clear sense into how this works. And so now that we have a better idea about this, what we're going to do now is we're going to dig deeper into each one of these models to see what kind of additional information we could get to accelerate our development process. So first thing we're going to do is let's actually, now that we've actually generated these models, let's actually take a look at them from a performance analysis perspective. So what we do is we provide full reporting. And so here what I'm going to do is I'm going to select the model that I've just created. So ResNet 50 ImageNet. And so here what you can see are the different circles, and it shows you the overall trade-off between performance, so in this case, top 1 accuracy, and flops, right? And so you can then pick and choose and analyze which one of these is good for you for deployment. And what you can also do is you could compare with different runs and different models that you create, so you can actually see what the underlying trade-offs are. So this is actually quite easy to use and intuitive. And so what we're going to do now is we're going to go through any one of these and go into additional detail. So here what we do is we provide full network visualization, so you have a full understanding into all the networks that are automatically generated by Jensen and all the trade-offs. So this differs a bit from what you usually see in TensorBoard. Instead of just showing connections, we actually show the importance as well as the performance analytics for each component of your neural network, so you can have a better idea into how it works, as well as the performance trade-offs. And last but not least, as we mentioned, because Jensen is able to generate different models, it also has inherent understanding on how deep neural networks work and its decision-making process. So what I'm going to do right now is click on here, root cause analysis, which allows us to go through the explainability component of Jensen. So with Jensen, it'll take each model that gets generated, and then it'll show you the different trade-offs and error scenarios. So in here, what you see is your conventional confusion matrix, which allows you to take a look at the different aspects, so where things are going well, where things aren't going so well. But what we do is well beyond what a confusion matrix can allow you to do is the level of explainability. So if I were to click on any one of these, let's say in this case, I'll go for iPod. So in the situations where it determines that an iPod is an iPod, so it does it correctly. And we want to make sure that it's making the right decisions for the right reasons. So let me reshare my screen. And so can you see my screen?
Yes, we can.
Okay,
yes.
Perfect. So what I did was I clicked on the iPod element in the confusion matrix. And then what you can see is that right off the bat, instead of the usual way of actually going through your data, going through lots of scripts, going through it one by one, which is a very laborious process, what we do is just by clicking on this, we're able to show every single error scenario and every single correct scenario that you have in your data set with just the click of a button. So here are all the examples where there are iPods and they were determined as iPods. But beyond that, what we can do is if I click on show overlay of root causes, it'll actually show you the critical factors determined by our underlying explainability to identify what are the critical factors necessary that the model is using to make decisions. So this gives you a quick quick overview to make sure that it's actually making the right decision for the right reason. And so if I were to click on any one of these, for example, this one, what you can then see is what's different than, about what we do from an explainability perspective is by leveraging our proprietary explainability approach, we're not only able to show you qualitatively the critical factors involved, but we're also able to show quantitatively the level of influence that these critical factors have on the decision-making process. So if you see the actual purple lines on the right, it shows you the prediction confidences when your model is focusing on these critical factors, labeled here as with root cause. And so, great. So how do we actually know this is actually important? And this is actually one of the key defining factors of our explainable AI compared to some of what's out there right now. Here, not only does it tell you what it is, it also tells you what happens when you're looking at it and when you're not. So in this case, when the model is not focused on the critical factor, here in pink, without root cause, it shows that when it's not focusing on that, it starts focusing on other areas that leads it to make the wrong decision. In this case, when it's not looking at the critical factor, it's actually focusing on the screen of the iPod and it thinks it's actually a printer. And as you see, if you have a lot of different, let's say, laser printers and so on and so forth, their display panel looks kind of like that. So now you have a much better understanding into how your neural network is actually making decisions, so you can see where are the issues and where are the problems, whether it's a human problem, whether it's a model problem, or whether it's an annotation data problem. And last but not least, I'm going to illustrate it using a more exciting case, and I'm going to illustrate based on object detection for autonomous driving. So here what we did was we went through the Jensen process with a object detection system trained around the KITTI dataset for automotive based object detection. And here, one of the interesting parts here is that with a classification, sorry about that. With a classification task, it's actually quite easy to decompose the different error scenarios. However, as you know, with object detection, each scene can have very different objects, and it could have multiple objects at different locations. And traditionally, there's no way to do confusion matrices and so on and so forth around it. But with the Gensive Explain platform, what we've done is we've built proprietary algorithms for taking scenes and decomposing it into its different elements and identifying all of the different error scenarios based on the individual components, and then re-expressing it in the form of the confusion matrix. So for example, what you see here are all the scenarios where a pedestrian might be I guess, misidentified as a cyclist, and vice versa, a car missing. But this is typically very difficult to do for object detection cases. It's also rarely done. And here we built an automatic way for automatically decomposing it into error scenarios. So if I were to click on any one of these, for example, we're going to look at cases where it's supposed to be pedestrian, but it was predicted as a cyclist. If we could click on that, then what it's going to do is it'll actually load up all of the scenarios within where there's a scene where within one of the components, there is a pedestrian that's mistaken for a cyclist. Again, this would usually take a very long time to diagnose. Here, we're able to provide it within the click of a button. And just to confirm, I'm going to show the bounding boxes. And as you can see, these are all the scenes that have this error scenario. And now what I'm going to do is I'm going to click on one of them. And here is actually a very interesting case that would otherwise be very difficult to identify in your standard deep learning development cycles. So here we have a pedestrian, right, as labeled by the human annotator, but the model thinks it's a cyclist. And the interesting part is that it's actually a cyclist who got off her bike, and she's walking her bike like a pedestrian. And these are important cases to understand because they represent outlier cases that we need to account for both in the model and data side. And so by using Gensive Explain, you're able to get a better sense of where the error lies, whether it's on the model side or the human error side or the data side. And of course, as I mentioned before, because Gensive is able to decompose these scenes into individual components, this is just one of the many errors in this particular scene. So what I'm going to do is I'll click here. And now what I'm going to do is I'm going to look at other error scenarios. So for example, if I were to click here, what you'll see is that within this scenario, not only was there a pedestrian who was classified as a cyclist, we also have a scenario where the model is able to detect all those pedestrians correctly. However, there's no labels assigned to those pedestrians. And so instead of your typical model error, what we have here is a human annotation error. So now you're able to easily identify these errors. And instead of correcting your model, you pass it back to the human annotator to get them correctly annotated. Because as you know, with models, it's only as good as the data that you feed it and the annotations that you provide it. And so in general, here is a overview, a walkthrough of the Gensive platform. And an illustration of how we leveraged it in a human-machine collaborative approach where we treat the AI as the collaborator to accelerate the deep learning process instead of taking months to years to days and weeks. So thank you very much for listening, and I'm open to any questions that you might have.
Alexander, so it looks like there are a couple of questions in the chat.
Sure. Let me go through them. Okay, so the very first question is, how does it choose what kind of paradigm to use? So the answer is, what you do is you provide a model prototype, and that's what it learns from. So for example, in the computer vision use cases, what it does is when you provide it with, let's say, a prototype that's geared more around convolutional neural networks, then it learns and understands that you have a vision task that a convolutional neural network is the preferred direction that you would like to go into. And then what it'll do is then it'll start automatically generating convolutional neural networks that meet your, I guess, your target operational requirements. Okay, and the second question is, at a certain point in the configuration step, I select a model. Are the generated models variants of this base model? How is this related to AutoML? That's a very good question. So what Jensen does is it learns from the model prototype that you have crafted, and then it'll generate models by learning from it as well as your underlying data. So when it generates models, there are models that you'll actually learn from your underlying setup. And so they bear similarities to your provided base model prototype. And that's what the prototype, it helps guide it to solutions faster. But you'll notice significant both macro architecture as well as micro architecture differences, especially when you use the edge option, in which case when it's catering for the edge, it can look very different than what you provided it. But again, the short answer is it learns from the model prototype that you provide, and then it generates models based on those learnings. So how to deploy the model? Will Jensen generate Python code automatically? So what Jensen does at this current stage is it generates what we call computational graphs. So for example, when you're using, let's say, Keras or TensorFlow, what it does, it actually generates a TensorFlow graph for you to use directly. So in which case you're able to access as input tensors, output tensors. You could connect it to your MLOps pipeline. You could make further modifications to it. You could continue to train it or customize it outside of the platform. So it's essentially a computational graph that you can do however you want. So does the platform have ways to address imbalanced data? So currently we provide all the tools for you to actually handle that. So we've had situations where you have imbalanced data set. We provide the full customizability for you to leverage things like, weighted losses, batch balancing and so on and so forth directly in the platform. And moving forward, we're going to incorporate a number of intelligent augmentation capabilities that we've been developing into the platform. So that will also then allow you to automatically deal with situations like this. How do you ensure the platform doesn't miss the best model? Maybe there's a better paradigm with different hyperparameter configurations that can lead to better results. That's a very good question. And so what we do is by using a generative learning process, what it does, it uses all information that you provide to try to identify the best models that meet your particular requirements. As well as provide all the trade-offs between them so you can then pick and choose. There's always never a guarantee the absolute best model, but by taking into the human-driven operational targets that you have, it will generate you for the best model to meet your particular requirements. So there's a quick question about trying the platform for free. So that's something that we're considering right now. So that's something that I could probably, if you connect with me, I could forward you that question to our sales team. Okay, so in the Audi use case, where did most of the improvements come from? Okay, so most of the improvements stemmed from the macro architecture and the micro architecture designs that Jensen was able to generate based on its learnings from the model prototype. So for example, in the generated models, it had fewer components, fewer graphical graph nodes as well as edges. It had fewer, or let's say, convolutional components, so therefore allows for lower computational complexity. So it's a combination of different things. And by taking an automated approach, it allows it to be tailored for those particular performance needs. So it doesn't need packaged ML flow inserted into, no, it doesn't. So the question here is, does it need to be packaged and inserted into Jensen? What you really need to do is essentially, for example, if you're using Keras or TensorFlow, what you just need to do is provide the model prototype in the form of a metagraph. Can you generate model with different architectures? The answer is because it takes a generative approach. It does inherently generate models with different macro and micro architecture designs, customized for your particular needs. Is it better than neural architecture search? I would say we take a different approach, mainly because with a lot of neural architecture search, what you end up with is a complexity trade-off between the search, the size of the search space, as well as the computational complexity with doing that search. So you'll see many situations where for large search spaces, you're essentially searching for, with hundreds of GPUs, TPUs over the order of weeks, and that is usually too computationally complex for most use cases. So what we do is by taking this general approach, we're able to do it in orders of magnitude less time while still providing these good models that meet your requirements with different architectural trade-offs. In terms of is Gensive leveraging reinforcement learning? The answer is no. It's based on our approach that we call generative synthesis. And if you look that up on Google, you'll be able to find the underlying paper related to it. So just as a short summary, so the generative synthesis process is based around the interplay between a generator and a inquisitor, where the generator generates neural networks and learn to generate them better and better based on feedback from the inquisitor on how to improve. And the inquisitor keeps observing different models that the generator builds, and it gets better and better at understanding deep neural networks. And so both get better in an iterative manner, and as a result, you get better and better models over time and better understanding around it. So do you provide it for students for learning? That's actually something that we're considering. And we've actually done a number of different pilots where we've had students use it to great success. Inference process, inference latency, GPU accelerated, CPU only acceleration latency distributions, so on and so forth. So related to that particular question, so which is asking about things like the performance metrics, as well as GPU acceleration, CPU acceleration, latency distributions. So what you can do is you can specify all of that in your custom performance metric. So because we provide a full Python scripting interface for you to define your performance metrics, you can define any of these as your performance metric, and then Gensive will then learn from it. And that's where the flexibility lies, because what we're creating is a deep learning development platform. One of our goals is to give you full control on how you want to create, what your specifications are, as well as what your requirements are. And so therefore, by giving you the full power to enter them, Gensive can then learn from any of these particular performance metrics that you specify. So how much is the platform, and does it run on AWS? Do we have to pay AWS separately? So what we do is we sell a platform, and it's a containerized platform. So it does run on AWS with the actual walkthrough that I just did right now. It's actually on AWS. So I did the entire walkthrough with the platform on AWS. In terms of pricing, that's something, if you contact me, I could connect you directly with our sales teams on that. We have different pricing schemes depending on your needs. We try to be very flexible around that. And in terms of, do you have to pay for AWS separately? Because we're selling a platform, not as a service, but as a platform that you could deploy however you want, be it on the cloud or on your local on-prem servers. If you want to deploy it on AWS, you would have to pay for AWS separately from the software license. And so the question is, how can I contact you? So you can actually contact me at Alex, A-L-E-X, at darwinai.ca. Generate and grid search for new architect. So, one of the key things is that if you look up the generative synthesis paper that we put up, what you can do is you'll get you'll be able to see further details. So it does not actually do a grid search. What it does, it takes a learning-based approach, and it learns, essentially the underlying premise is that you'll learn generators, right? And those generators are then able to generate better and better neural networks based on the operational requirements that you provide, as well as from the learnings of the inquisitor. So give me 1 sec. I'm going to stop sharing my screen. And I'm going to now provide a link for you to learn more about it. So here's the paper that we've presented. And so you'll be able to get all the information you need about the underlying technology behind it. So another question that was asked is, what if I want a lot of compute power for my model? Does the platform provide compute as well? So our actual platform is a software platform that you deploy either on your local computing servers, your laptop, or on the cloud. So whatever compute power that you need will be provided on your end. Our platform will just leverage that compute power to generate better networks for you. I hope that answers your question. Okay, so a lot of companies have struggled with explainability. What was, oh, sorry, let me just paste, sorry, I just realized I sent a private message. So here is the actual link to the paper. And so now I'm going to answer the question. A lot of companies have struggled with explainability. What was Darwin's breakthrough explainability? I think our biggest breakthrough with explainability actually lies from our ability to generate neural networks. So a lot of the explainability approaches out there right now are what we call proxy-based approaches like SHAP and LIME, where they treat, I guess, the model as a black box and try to explain this black box. And so the problem with that is there's a lot of stability issues that could come from it. You might actually get a different explanation each time you ask. And so if each time you get a different explanation, then it's hard to trust that explanation. It also doesn't have internal understanding on the actual process with which, let's say in this case, neural networks analyze data. And so because of the underlying GenSynth platform, because of the underlying GenSynth technology that actually learns to understand the intrinsic internal properties of neural networks and how they behave and how data propagates through neural networks, it's able to give a much clearer understanding, a deeper understanding into how they make decisions. And so we're able to better surface it through DarwinAI's explainability. And so our explainability is tied directly into our generative synthesis process. So that's where the inquisitor part comes in. Yes, so just give me 1 second. So someone is asking if we have paper on the explainability. We do. So I'm just going to paste a link to it. And this is where we actually compare what we do with a number of popular approaches like SHAP, LIME, as well as expected gradients to show that when we're making this, when it's actually given explanation, that it's actually better reflective of the decision-making process. So I provided the link in chat. So I guess if there's no other questions, I'd like to thank everybody for attending this workshop, and I hope you enjoyed it, and I hope you got a good sense into how GenSynth works and how we're able to leverage it to accelerate deep learning development to really streamline MLOps, and looking for future opportunities to work with all of you and hope you'll be able to leverage GenSynth for your particular purposes. Thank you very much.
Thank you, Alessandro, for a great talk. Thank you, everyone, for joining. Once again, the recording for the workshop will be shared after the summit, so please look out for an email. Thank you, everyone.
Thank you. Have a good day.
Sure. Bye.